Let's see, are we live? Hello, 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 hello. Howdy. Hello. Hello. Are we here? Yep, believe we're here. So hello and welcome. Guten Abend, good day. Here we are, another day. Another beautiful day. I have some, what do you call it? I have something I wanted to say before we started going. So we're going to go ahead and get into part 3 of our problem we were looking at the other day. And we're going to look at the discussion that other people have to say about this problem, and also their solutions. There are probably other better solutions than the one that I have, obviously, clearly must be, as much as I appreciate what I came up with. So yeah, let's do that. And do I have any other comments? Not really. I mean, there's a lot on my mind, a lot on my plate, but for now, let's just focus, I guess, on solving some problems. So let's do that. So here we are. This is Reconstruct Itinerary, part 3, number 332 medium on LeetCode. And I'll give it a plus because I'm grateful that I got to see this problem. And we have a solution. I believe it's correct. And it's kind of slow. Uses a bit of memory. I don't really know what a better solution would look like. I don't know. So I'm going to go learn from some other people here today. And what I did was, so let me read the problem. We'll start with that. Given a list of airline tickets represented by pairs of departure and arrival airports from and to, reconstruct the itinerary in order. All of the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has a smaller lexical order than JFK LGB. All airports are represented by 3 capital letters IATA code. You may assume all tickets from at least one valid itinerary. Form at least one valid itinerary. One must use all the tickets once and only once. Okay. So what I did was I said, all right, this is a lot like a graph problem. Each airport is its own vertex, and a ticket from one airport to the next is a vertex, and it's a digraph, a directed graph. So there's also sort of a from and a to, so from and to for each ticket. And the idea is, this is what they call an Eulerian path from the beginning vertex to the last ticket, the last airport, where you're going to traverse every edge, you're going to use every ticket. And there are some properties to Eulerian paths, and there's a whole kind of this, it's part of graph theory, we'll say it's been studied, And the solution I came up with was I said, okay, let's create an adjacency map, adjacency graph, where we, instead of using a vector of vectors, and we're going to use strings to strings, so we're going to use the keys are strings, and they map to a set of strings, and not just a vector of strings, but a set of strings. In fact, not just a set of strings. And the reason why I want to do that, and I'll explain in a moment, is so we're going to use a multiset, in fact, which is slightly different than a set, where you could have multiple copies of the same key. So you could have, so in a regular set, if you had 2 strings that were the same, they would be removed from the set because the set would basically condense to one element of that value, whereas a multi-set will actually keep 2 copies of that if you insert 2. And the reason I did this is because I actually missed this in the description of the problem. It's further down here. Oh no, we have the notes. Yes, yeah. So if there are multiple itineraries that are possible, what we want to do is there might be multiple different Eulerian paths that are possible. We want the one that, if you were to kind of write out the string, or if you were to concatenate the whole string for all of the airports, the lexicographically smallest string that you would get is the path that you want to take. So by throwing these things into a multiset rather than a vector, simple vector, it would automatically sort based off of lexicographical order. And so we would always have the first element that we look at would always be the lexicographically smallest valued edge from the airport to the sort of all the, so from any particular airport that you might want to pick another airport, it would already automatically, it would be immediate that you would have the lexicographically smallest airport to go to. So what I decided to do is I said, okay, let's create a graph in that way, in that fashion. And now we have, from each vertex, we can easily know what the neighbors are, what the possible choices are based off the tickets that we have. And then I said, okay, let's do a depth first search where we pick the lexicographically smallest airport to go to. We go to that one, we update our graph by removing that ticket and removing it from the multiset, and then recurse on the neighbors from that vertex, from that point. And basically at each step you're going to remove one piece of the graph. You're going to remove one vertex. At the same time, when you finish your recursion, you're going to reset the things that you modified. So you're going to we would also be building our resulting vector, basically the list of airports. We're going to build that as we go. So when you actually jump to the next airport, you would add that to your list of airports. So the vector of airports, it's a vector of strings to represent the airports. And then when you finish your recursion, you want to go back, you remove it from the list, you pop it from the back of the vector. And so going in, you remove the edge from the graph and push a new value to your result vector, and then once you finish your recursion, you're going to pop that value off the resulting vector and add that edge back to the graph, right? Because now we're sort of going back to the previous state. And what I realized is that you can do this exhaustively, so you could find every single possible path, and check when you have basically the right size for your list. So there's sort of a running total of all the airports that you visited, and in the order that you visited them, you have this sort of number of like how many airports did we visit. When that's a certain size, you can register that as, okay, we've used all the tickets, and then you can check that against. You could check that against a running tally, which is basically you have so initially you don't have any path that you know of, and so the first one you see you would make it that path, and then as you see other paths, you would compare those paths against your best path so far, specifically the lexicographically smallest path you've seen so far. Now, what I realized as I studied Eulerian paths a little bit more and what the properties of the graph you'd have to have in order to have a path. And I learned that actually, if you do it this way that's described, the first time that you have a path that exists, you can actually stop right there. If you perform it exactly in this way, it'll always be guaranteed to be the lexicographically smallest. And the reason for this is that the only reason why the reason for this is that there's sort of like an ending point that you're going to have for your path that'll always be the same no matter what path you take. And if you reach that ending point and you haven't used all your tickets, you have a problem. And that can happen. However, it's only going to happen once if you backtrack, because if you backtrack from there and you don't take that path again, the very next path is guaranteed not to cause the same problem where you don't use all the tickets. It's exactly only one way that you could end up not using all the tickets, which is a pretty interesting and clever and kind of like a pretty creative way to solve this problem, realizing that that's the truth. And I'm pretty proud of myself for figuring that out. I thought that was so clever. So you only need to backtrack once, and in order to so actually not even just backtrack. Well, you only have to backtrack once. It's the first time that you actually get to, or you may have to backtrack more than once. I'm sorry. It's possible that you need to backtrack more than once, but the first time you actually reach that ending state with all the tickets in place, that's guaranteed to be the lexicographically smallest, which is the answer you're looking for. Lexicographically smallest path, or Eulerian path. So we can run our backtracking algorithm, and then we can just basically set a flag that once we find the first Eulerian path that uses all the tickets, we can basically for all the other iterations that we might do, just check that flag and exit return, just get out of it, finish. That's great. And so that's what I did, and it seems to work, and I feel great about that, because I basically figured it out on my own, and I like doing that. It's a good feeling if and when you do that, and so feeling a sense of accomplishment. Now, naturally, there's a better way to do this, must be, and we're going to go ahead and take a look at the discussion and find out what do other people have to say. Better way to do it. So here's a C++ solution, Java, DFS, simple Python DFS, wrong test case, DFS iterative, no explanation. Oh, it's iterative. That's interesting. No recursive calls. Kind of curious about that. Beats 100% and short and elegant C++. Eulerian path and directed graph, recursive iterative. Let's see some of these. And new algo to learn, yeah, non-recursive. Linear time, linear space solution with detailed explanations. Okay, so let's see. Yeah, I like Pacman's. Usually this is quite good. Although we're not going to go over the Ruby and the Python, nor the Java either. Just stick to C++ for now. Oh, I used a multiset too. Interesting. Find itinerary, multiset targets route, JFK for a ticket, and tickets, targets, ticket first, insert, ticket second, pair, ticket, string tickets. Yeah, I guess you could rewrite this as such. I guess that makes sense. And then each ticket, targets, ticket, insert, ticket. Did something like this. Visit JFK, route begin, route end, reverse the route, visit the route, visit while airport size target, okay. Targets, next equals begin, erase, visit next, pushback airport. Wow. Wait a second. This is pretty interesting. I notice he doesn't push anything back into this set. I gotta think about this. What is going on? First, keep going forward until you get stuck. It's a good main path already. Remaining tickets form cycles which are found on the way back and get merged into that main path. Okay, first keep going forward until you get stuck. Right, which you should get stuck initially. That's a good main path already. Remaining tickets form cycles which are found on the way back and get merged into that main path. By writing down the path backwards when retreating from recursion, merging the cycles into the main path is easy. The end part of the path has already been written. The start part of the path hasn't been written yet. So just write down the cycle now and then keep backwards writing the path. Example, JFK, A, D, B, C, A, C, D, JFK. From JFK we visit JFK, A, C, D, A. There we're stuck. So we write down A as the end of the route and retreat back to D. There we see the unused ticket B and follow it. D, B, C, JFK, D. Then we're stuck again, retreat and write down the airports while doing so. Write down D before the already written A, then JFK before the D, when we're back from our cycle at D, the written route is DBC JFK DA. Then we retreat further along the original path, prepending CA and finally JFK to the root, ending up with the root JFK AC DB C JFK DA. What? Borrow your brain for this upcoming interview. So I'll give it back right after. Very impressive. I don't know what he's on about here. Totally straight over my head. Totally over my head. Not a clue what he's talking about. I don't really know what this does, and the explanation I didn't get either. So we're gonna have to sit and think for a while, ponder it. Okay. So this part I get. This creates our multiset, right? Fair enough. And this gives us our recursion, and then this reverses the root at the end. All right. This only gets called once, so that's fine. This gives us we start with an airport. We say get. We have our, while there's still tickets, do this iteratively. We're going to set next to be, we take that path, we say erase it, that ticket, gone, right? And we also, now for this airport, now we visit next, we visit that one. So we also write to our root, this airport. But, however, this is important. This gets written after the recursion, right? So this is after you do your visiting, JFK, you're going to push into the back. You're going to put JFK. So there's going to be a whole bunch of stuff that happens in the interim, but on the back end you're going to put a JFK there. So you know you're going to visit JFK. Okay. Now you say, all right, there's some, let's see, from JFK, there's like a B or an A. Well, with multiset, we're going to do A first. So we visit A, and we recurse. And we say, okay, A still does have at least one place to go. C, one ticket. So we're going to remove that ticket. We're going to set next to B, and also we've queued up A to be pushed onto, so now we've got basically A is prepended before JFK, right? It comes before JFK, whatever the coming before route looks like, we've got A placed in there. Okay, fair enough. Now, what's really interesting about this approach is it's very similar to my own approach. However, it's slightly different in that you don't need to maintain the whole list, the whole map. Like, he builds the whole map. However, you don't actually need to keep the whole map. He actually destroys most of the map, if not the whole map. Excuse me, once he's done here. In other words, all the memory goes to 0 at the end here, so he uses all that. So his memory usage is a lot less than mine, because sort of the way they measure it, because it's the same sort of overall amount. It's a linear amount. However, it's a linear amount of memory. However, it's less sort of, I guess, in practice, something like that. So it's also a much simpler implementation. This is super simple, but it's very similar to what I did. So I'm glad it's at least similar. So now he's saying at some point you're going to get stuck, right? And let's say before we get stuck. So we kind of dig in, right? We have a cycle. JFK, A, C, D, right? And these things are all going to be backwards being written. And then back to A, right? JFK, A, C, D, A. And then the thing is, there's not going to be any tickets at A, right? We're going to write A. JFK, A, C, D, A. There's not going to be any tickets there at A anymore. and we write A. Now, what's interesting is that he doesn't pop anything, right? Like he uses this whole cycle and gets stuck there. And I guess what's interesting is what he's suggesting is that you can use just before A would be the next, right, the previous airport. If that has tickets, you can add those tickets now, right? So, and before you write this A, you'll actually end up writing that D, I believe, right? Am I right? Am I crazy about that? Let's see. When you look at D, when you push back D, you would push A before you push D. JFK, so you have JFK, A, C. Now this D and this A is interesting because we know whatever happens after A is going to come before A. Whatever happens after C is going to come before we write C. Whatever happens before D is going to come before we write D. And actually, before you write D, you do A and B, right? And A does come before D, I think, right? So this is sort of JFK, A, C, D, B. I see, right. So that's kind of the iterative nature of this, is that before you write A, you would actually write B, C, JFK, D, and then write A. This cycle would happen before A. Even though A comes before B in this loop, see, that's really confusing. When you get stuck, you would retreat. But you're writing this onto the back. And you're writing it onto the back of the array. You're writing on the back of the array after everything is done inside the loop. So we didn't write A yet, or excuse me, we got to D, we processed A and B before we wrote D, right? Process A and process B and then write D on the backside, right? But for some reason, B ends up getting written before A. And I believe the reason B gets written before A is we visit A, and then after processing A, we push back. Now that doesn't really make a lot of sense to me. I would think I don't really understand, actually. I want to say that we end up writing A before B. Push back this, push back that, push back C. We don't actually push these things back though. We push them after we've pushed everything else. We push CA and JFK, right? After JFK gets processed after A gets processed, and then A gets pushed after C gets processed, and then C gets pushed after D gets processed, and A gets pushed after D. Okay, well, I see. Okay, yeah. So A gets pushed after D gets processed. Right, that does make sense. And then D, yeah, okay, that does make some sense. Just thinking, how does that work? It's or C gets pushed after it's processed, which means you've got to do something with D. You got to visit D first, and then D gets pushed after it's been processed, which means you visit A and B before you push D, and you yeah, see, that's what I'm saying. You don't. Yeah, no, that doesn't. Am I crazy? Am I nuts? Am I nuts? Why does this feel like this doesn't work properly? It doesn't work the way that I think it would work. Hold on, what? So let me see something here. I think I already saved this. That's what I'm looking for. I think it's. Okay. Yeah, just wanted to check. So what I want to do is I want to try this. See if I can get this to work here. Does this not work anymore? I mean, you could pretty easily go to vectors. Just do ticket 0, ticket 1. I was kind of wondering how he did that with the pairs. So this seems to be correct. I'm afraid I don't want to hit the button because it's not my code. Although I'll probably end up writing a similar thing anyway. Oh, okay. Give me 1 second again. Alright, the example that he gave is this. JFK to A to B. Bada B, bada B, bada B. Well. To B. To, no. C. C. D. B, C, back to JFK from C and up to D. So we got A, C, D, and then D goes to A too. All these tickets. All right, it's got 2 out, 1 in, and this is. Two out, yeah, 2 in and 1 out. So we go from JFK to A, and he's saying we're going to end up with, we've got 1, 2, 3, 4, that cycle, We've also got 1, 2, 3, 4. Oh no, 4. Yeah, to D. And then what we want to do is what we want to do from here is his algorithm, right? So let me just get all the tickets, right? So that's the thing. I want them tickets. Want them tickets. JFK to D, D to B. Hopefully I got this right. B to C, C to D, D to B, B to C, C to D. I want D to A. I don't really understand what he was getting at with this. I need see a few examples, I think. JFK to A. Let me see here. C to JFK and A to C. All right, how many tickets we got? 1, 2, 3, 4, 5, 6, 7, 8. 8 tickets. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's see. Wow, it's so fast. And it's right, it's correct. Now how, I don't get it, man. I don't know. I don't, Nope, not getting it. Obviously this is super fast. You can see it. That's extremely fast. How? That don't make no sense. It don't make no sense. Well, what we can do, we can like basically print this debug to find out, like, understand what's happening here, get a better idea. So we can say root looks like the following. So I'm interested, so we get A first. Oh. Huh. That's so weird. The first thing that we write is A, then we do D, JFK, C, B, D, C, A, JFK. Is that what we expect? First thing that we stop at is A, so we do write A, then we write D. Oh. that's so interesting. Once you get stuck, you start writing stuff. Oh man, dude, this is wild. This is like, it's making my brain freaking. Oh, let me take that out so you're not hearing the distortion. That's fun, man. I like that. That's awesome. That's so cool. Oh, so once you get stuck is when you start writing, right? And that's fine because that's the yeah. Oh, that makes sense. Oh, I was thinking about that. Well, because that's what I did. Right? I did something very similar. I said, all right, when you get to the end, you're going to backtrack. The next thing you get should be correct, right? However, you could be even more clever about this and oh wow, that's super interesting. More clever about this. Oh, this isn't O of n, by the way. People are writing that this is like O of n, these algorithms. Not true. These are not, they're O of n log n, something like that, because, or not, I don't know how to say it exactly. Basically, because we're using a multiset, there's a sorting going on here. Excuse me, that is actually relevant, but that's beside the point. So it may actually not be. It might be somewhat. It's not negligible, but it's. I don't know what the exact amount is, but it's not exactly linear, but it's fast. But anyway, so the thing is, right, when you the ending, the portion at the end that you got stuck on, that piece is going to be correct for the ending result. It's going to be the same, right? As he said, the part that's not right is the beginning, the portion before that, and so the backtracking, it should actually write that correctly. Or for me, the next backtracking is gonna write that correctly, and then it'll have the same ending portion in my algorithm. But in his algorithm, it's actually, you don't need to do any really. It's not really backtracking exactly. It's sort of like you keep going until you get to the end, right? Until you get stuck. And then what you're going to do is you're going to write those backwards. However, you're also, since you're writing at the end of the recursion, you're also going to process the rest of the graph, the rest of the other cycles, and then write those. And then, write the rest of it. And then everything's going to be flipped backwards. And that's going to be correct. What? I would never have thought of something like this. I don't know, man. That makes my head hurt to think about. That's really clever. That's like, I don't know. That's, wow. Huh. Yeah, it's a lot cleaner than what I had too. Really got to think about that. Oh, man. What does this do though? Why? So we do write A before we write D. That's what I thought. I thought we write A before we write D. And we write JFK before we write C. Then we write B, then D, then C, then A, then JFK. Yeah, see, that's really interesting. We append JFK to the end, we append A to the end, C to the end, then D, right? So that was his explanation. He was saying, oh no, wrong one. Oh. So I was saying, right, we append JFK at the end, then we append A at the end, then C, then D, JFK, A, C, D, which is exactly what I got. Oh no. Uh-oh. Oh no, did we lose it? No! Ah, it took so long to put that together. So I could probably do it again now. JFK to A to C, C to D, and from D to B, from B to C, so that's, yeah, C, D, D to B, B to C, C goes to JFK, and JFK goes to D, and D goes to A. I think that's it. 1, 2, 3, 4, 5, 6, 7, 8. Is it 8? I think it's 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we got them all. Let's see how we do. Okay. Yeah. JFK, A, C, D, B, C, JFK, D, A. So we write, so what I was thinking was happening, right? So let me just look at this picture and look at the code here. And just kind of follow. And actually we do want, oh, no. We do want something else here we can write. Make this font a little bit larger. Okay. So this is what we get. All right. So here we are. All right, so here we are. Whew. We visit the airport, we visit JFK. We said we're going to come back and we're going to write JFK after we write everything else, which is exactly what I was expecting. They visit A, same thing, A would be written. Visit C, C is written. Visit D, D would be written before these other things, or yeah, after all these other things are written. But what's interesting is that this is the part that really throws me off. B gets written after A, or B gets written at the end, appended after A gets appended. So B actually gets written later than A, right? And that is really interesting to me because when you get to this part of the code, this next equals this targets, it's going to be A. This is going to be the beginning for airports of D. It's going to be here. It's going to be A. You erase that ticket, and then you visit on A. And then A, at that point, shouldn't have any other tickets, right? We hadn't written anything yet. We wrote A. And this is the first thing that gets written to the whole thing, right? That's sort of at the very bottom. And right above that A is D, which you actually end up writing D next, which throws me off because I was expecting, so you write A, you push A, and you come back, and now then, and you do have another target for D of B, and now your next should be B, and you say erase target B, visit B. And the reason why B doesn't get written next is because you end up cycling all the way through back to D and write D. That's why. That's why you write D next. Oh, that's really interesting. So you end up writing at D this whole cycle, which actually brings you back to D. So you write D, JFK, C, B, D. Boom. Oh man, that's so clever. Oh, I see, I get it now. I get it. Because you're going backwards. You actually do end up writing this D before anything else. Believe it or not. You write this A. First you write the A, then you write this whole cycle, which ends at D. And you wrote it backwards. And then, right, so this is A to C to D, which fails at A, which writes A, and then doesn't fail at B, writes the whole cycle, and then you append the rest, C, A, JFK. Right, the rest of your cycle, basically, gets appended. Now, how do we, okay, so I understand that now. That's really interesting, but how do we, at least I understand that on a superficial level, but how do we understand that? How do we understand that as, like, if we're going to write our algorithm for this, how do we take advantage of this? Like, how do we think this up on our own? How do we figure this out on our own? Realize this? Like, how do we describe this in another way that's like easier to remember or digest or understand? Basically, the cycle, we write, I don't know, man. I don't know. We're doing a post order. It's a kind of a post order traversal, right? That we push back after we traverse. So it's post order, and it's a post order over the children, and we're also removing the children as we go. And somehow this gives us the solution that we're looking for. Like, I don't know what to say about this. Like, it's just something about it is really special. It's definitely not something I would have thought of. So I guess post orders and cycles, you basically, in a post order, if you write in post order, you pretty much write the thing that you're working on backwards. You're working through. You end up writing it backwards, right? That's kind of what ends up happening. I want to say that's the case, right? If we do a post order traversal of a tree, if you said like A, or just 1, 2, 3, 4, 5, the post order traversal is gonna write 4, 5, left, right, 2, 4, 5, and then 2, and then 4, 5, 2, and then 3, and then 1. Right, post order. 4, 5, 2, 3, 1. Right, and if there was a cycle, you're doing post order, where you remove that cycle, you would go starting from 2. Let's say 2 would come after 4 and 5, and 4 would come after 5, and so 2 would come after 4 and 5, which would be exactly reversed. And the reason it's so useful here is that you could end up going somewhere and you go one way, 6, 7, 8, let's say, and then you basically get stuck there. The other children, let's say this is the first one, you take this one first. The other portion, let's say, I don't know, let's say we started at 1 and we went to 5, and we do this post order. This 6, 7, 8 is actually going to come after the other parts. What's weird about this is I'm just thinking about, like, what if that wasn't the one you were supposed to go to first? Like, what if that was the one you'd go into last? Like, you did that part, you traversed the other cycle. I guess you try to do it afterwards. Like, basically in this example, it just so happens that A is a better option than whatever the other option was. Well, no, see that, no, it doesn't matter, right? Because whatever cycle you take, I guess you are always going to end up like, actually the best, the greedy approach, like the best possible approach is always going to you're always going to end up, either you're going to cycle through the whole thing in one giant cycle, or you're going to stop at some point, and then the other portions are all going to be cycles as well. I mean, they have to be cycles. Yeah, either it's one gigantic cycle or it's broken into multiple cycles. And the part that takes you to the end, right, as I said, yeah, if basically you're going to go through some number of cycles before you reach the terminating cycle, we'll call it. And then you may have other cycles as well, and those will end up coming before it. So you can kind of break it into multiple pieces, really. Each cycle you go over will sort of just come one after the other in the right order. Really interesting, fascinating. Fascinating. I don't think I would have thought of this. I don't even know if I would think of this again if I was faced with the same problem. If I could, I mean, I would remember this solution, but I'm not sure if I could think it up on the spot because it's so strange to me. You know, it's so odd. It's like you have, first off, you have to really know your Eulerian graphs or Eulerian paths, because you would need to have you need to know that these are all cycles. The path that you end on isn't a cycle, and then all the other ones are cycles. And then using a pre-order traversal of each cycle, it'll actually give you the entire thing before you kind of come back to the next. It'll write the entire thing before you come to the next spot. Really interesting. I think let me see if I could code this idea up myself. I mean, I think I got it, but it's really something else. So yeah, let's think about this. So we want to have, we just need the, so what I would do, oops, I need to do that. Okay, so what I would do is probably this first, because I tend to do that. And vectors and strings. Not going to modify these tickets. We're going to say for auto t in tickets. I'm going to say we have, so as a, yeah, so a, not a vector, but a unordered map of strings to multiset. We want to store our strings in. And we're going to call that G for graph. We're going to build the graph. We're going to call it S or, yeah. Or we could just A and B. And they don't need to be references, I think. Then we say G of A dot insert B. Right, so that builds our graph. And then we're going to have a recursion. It's not as much of a DFS as it is a recursion. And we're going to have a solution vector. Return vector. Reverse it, right? And we're going to say recurse. And we take a const string reference airport, or just next, or even stop. I was using stop before, but airport is probably fine too. And we're going to say while not, it's going to be G of airport dot empty. We're going to say const standard string s equals G of airport dot begin. Dereference. And actually, yeah, well, okay, yeah. We're going to say s, and we're going to say recurse. And we're going to say ret.pushback. Hold on, we'll get to that in a second. And we want to say f of sf, and also g of airport dot erase G of airport dot begin, right? So we're going to erase this ticket for that particular, this airport. And we're going to say while we're not empty, we're going to grab a ticket, grab a ticket, right? Grab a destination from this vertex, delete that ticket, and recurse iteratively right over all the tickets. And we're going to push back the airport. After we've processed everything, we push back this airport at the end. And this, and we start off at JFK every time. And this should give us the answer we're looking for. Or set, I think it's multi-set set. And MP is not, it's not how you spell empty. And cannot be used before it is defined. What's wrong? Oh, deduced return type. Gotcha. Void, I think. Wait, why? Why can't you reverse this? One more time. Oh, I'm sorry. Duh. That's my mistake. It's kind of a silly error on my part. There you go, it works. It's basically a copy of what he did. And it's fast. Use a lot less memory. Almost 100%. It's very quick. See if we can get it to just tick down and get us 100%. No, just not fast enough. Just barely not fast enough. What we can do possibly is, instead of using a multiset, we can actually sort the sort it backwards. The graph, and then we could pop back instead of erasing. Might be a little bit faster. I don't know, we could try that. Let's see if we can see what happens here. And then we can say for auto X in G, standard sort x.begin, x.end. Use a lambda function here. Turn A greater than B. We want to use const string. Could just do this too. Const string A. B. Then we sort backwards, right, using this lambda function. And then now we can say the end, really, g dot back, and then pop back. Right, something like this. Does that work? Begin, end. Why? Wait, what? In a pair? Really? Oh, okay. Oh, I see. P dot second. That's a little confusing. Not G dot back, it's G of airport. You can also say const or just auto reference X. So you don't need to do multiple accesses. Is that still correct? All right, still right. Don't know if it's, oh, there we go, a little bit faster. That's what I was saying. Hey. That's a little bit faster. Almost 100%. So close. So close. Yeah. The reason it's a little bit faster is because the operations on the vector are faster overall than the. Basically, you only sort once instead of sorting twice. That's kind of really what ends up happening here. We have to get to 12 milliseconds if we want to get 100%. It's really not that much faster though. It's barely faster. Oh, we're so close. Oh, we got 12 milliseconds. Oh, 99.64%. We're faster than almost everybody. Just I think 8 milliseconds is the fastest. We're so close. We're so close. Man. Can't believe it. All right, anyway, that's pretty good. That's pretty good. I like that. So, yeah, slight optimization that you can make. Now, the deal is, this algorithm is very nifty. As stated, it's pretty interesting, pretty amazing. So what did we do? Basically, we realized that there are multiple disjoint sets, cycles, excuse me, and there's one section that we want to, that isn't really exactly a cycle, and we're going to write everything backwards. So each node that we visit, we're going to append it to the end. We're going to append it after everything else we've done. And effectively, we're going to end up writing, in the beginning, we're going to writing the sort of final loop, right? The ending portion, left to right. And then we're going to reach a point that's a cycle. And we're going to end up writing the whole cycle backwards, right? As we kind of back through it, and then there'll be other cycles that we end up writing backwards, and then that's going to bring us all the way back to the beginning, and then we reverse that whole thing to give us the path. That's pretty much it. Really amazing, really clever, pretty brilliant. I don't know if I could have thought of something like this on my own. I don't know that I could have. I'd like to pretend that I could, however, I don't know. So anyway, so let me, that's probably enough. I mean, do you really need to know more than that about this question? Short, 44 millisecond, no recursive calls, no backtracking. Oh, well, you could, by the way, you could do this iteratively by not using using a stack instead of all these calls. Doesn't really matter that much. Excuse me, actually you can use this as the stack, I think. I think this is the same idea, same algorithm. And it's the same algorithm. The difference here is, right, you're basically using a stack instead of like a call stack. That's what I was saying. So it's kind of the same thing. Yeah. It's not, I mean, it's iterative, but like it's not really, not too impressive as far as it being iterative, as far as things being iterative. Beats 100%. Not my solution. Mine's faster. Well, it's not really mine. It's kind of, it's not really mine. I wouldn't say it was mine. It's slight modification on Pachman's. Fleury's, actually it's Herholzer's, according to the wiki, it works like this. Keep going one path until stuck, then retreat and push the vertices along the route to a stack until it reaches the vertex that has alternate paths. Then go along that path and repeat the process. Assumption for this to work is there is guaranteed to exist one Euler path. This problem is basically to find Euler path of a graph. By the way, you could find the guarantee of an existence for an Euler path. An Euler cycle exists if every node has even in degree and has equal out degree and in degree. And then an Euler path is that there's exactly one node that has a difference between the even and the in and the out of 1, and then another node that has a -1 for the same difference. Right? They basically are symmetric. They mirror each other. That gives you guarantees a path in the same if you also have everything else as equal in and out degree. And not to mention, we're not really considering vertices that don't have any edges to them at all, right? I mean, we're basically not even considering those vertices at all. So priority queue. No, that's pretty interesting. So they made use of a priority queue, but you actually don't need to use a priority queue. I guess that's Pachman's addition to Herholzer's algorithm, something like that. I want to say. So this is basically. I guess that's why it's so clever. It's like I wouldn't have thought of Herholzer's algorithm on the spot. It's quite interesting. So that actually is Herholzer's. Okay, understood. Pretty amazing. Pretty interesting. Great explanation on YouTube. Yeah, that looks good. OJ, online judge. It's really cool. Yeah, should be the best. Popping the edges takes care of avoiding cycles, right? Semi-Eulerian graph. Yeah, amazing, amazing, amazing. Don't even need a priority queue for this. Don't even need it. The priority queue basically allows you to do this like iteratively, I think. Don't necessarily need a stack, I suppose. Something like that. I don't actually know how you do it with the priority queue. I'd have to think about it. Anyway, yeah, super interesting. All right, so these are all kind of the same, really. They're all Fleury's or Herholzer's. Basically, they're all like variations of that. Pretty amazing. All right, well, cool. I mean, I kind of knew that. I said that. I was like, I think we're gonna need to use, Herholzer's, and that's probably what we'll see in the discussion. And yeah, that was what it was. So I got a pretty good solution. Not the fastest. Not the fastest, but pretty close. Pretty good. I'll take it. All right. Let me go for this question. I believe, I think we did good. I think we did all right. So thank you all for watching. I will talk to you soon. I'm gonna just kind of hang out for a bit. I don't think I ate anything today. I think I went the whole day. I was so stressed today. I think I went the whole day without eating anything. Wow. Hasn't even occurred to me. Oh man. I don't know why. Well, I actually do know why. I'm like kind of generally really stressed out for a number of reasons. So let me go ahead and say thank you for watching. I'm gonna go ahead, end this stream, make myself some food, some dinner, and then stream again. Just pick another problem and keep going. So yeah, thank you again. Take care.